All right, welcome. Going over notes for chapter 1.5, titled Integrating with Substitutions. And generally, I'm going to call this a U-substitution or a U-sub for short. So 1.3 was the fundamental theorem of calculus, that big picture idea of connecting integration and differentiation. And then, very importantly, how to evaluate integrals. Okay. But we're only actually able to find antiderivatives of some of the really easy problems, like using the power rule and things like that. And so, since we only really have that right now and at our disposal to do these integrations to find antiderivatives, we need some more tools. And a u-substitution is definitely one of the most common tools we need. All right, so if we were going to try to find the derivative of this thing, if we need to do the derivative with respect to x of this type of a function, well, when we have functions inside of functions, this was like the perfect chance to use the chain rule. We would do like 4, use the power rule, bring that exponent down to a 3, and then divide by 4. But then you had to chain on, you had to multiply by the derivative of the inside, whatever's inside of this larger function. And the derivative of x squared minus 3 well, that's just a simple 2x. And so those would cancel there, and we wind up with a nice 2x times x squared minus 3 to the third power. All right, so one thing we kind of have as we move forward and what we look to is now we're trying to figure out how to integrate something that looks like this. Our goal now is to be able to go from this back to this thing. And I don't know about you, but I don't see how those two connect just by looking at them. I kind of see a little bit of a structure. I mean, the 2x or that squared minus 3 is in there. But to be able to go from this to this, go backwards, that antiderivative, well, we kind of need some help. And when they're kind of nested together like that, a composition of functions, we need some help. All right, the help comes in the form of this idea of a u-substitution. When you see kind of a function inside of something else, a composite function, what we try to do is let u, this letter u, be equal to this other function. And then hopefully we can take the derivative of that function. And it needs to be a continuous derivative. Okay, f is also continuous. Well, then when we take we have a function f with another function inside of it, hopefully we can work out where the derivative of this inside function is actually also part of the bigger picture. Okay, that allows us to kind of make this substitution and the function looks nicer. We might be able to find the integral antiderivative of that function and then kind of replace things back. So it's a little magic trick, if you will. All right, here's generally what this is going to look like. I see with this function, we have kind of a bigger thing. We have like something cubed. Okay, we've got that something cubed. Inside of the something cubed, I see this thing. So what we do is we say, hey, let's let u, this new variable, be equal to that. All right, what that's going to do for us, if we let u be equal to that, is now we kind of wind up having the integral of u cubed. And that's really nice. I know how to do the integral of u cubed. But the problem is there's still this other stuff. Now we have u's and x's in our problem. All right, so the u-substitution says, well, hey, when you're taking now the integral with respect to u, well, let's differentiate this. Let's find du, the derivative of our u variable. Well, to take the derivative of u, we then take the derivative of the other side. So derivative of this would be 2x derived with respect to x. 2x dx. Now, you see how this 2x dx perfectly matches this 2x dx? It's also part of our now integral. Well, we can substitute that out as well. All right, this becomes the integral of u cubed. This 2x dx gets replaced with what it's equal to, du. And now we have a really easy power rule that we can do. To integrate u to the third du, there's no x's involved in this integral, antiderivative, I should say, and so we can do that. Just the power rule. It'd be u to the fourth over 4. Right? Add 1 and then divide by that new exponent. Okay? Plus c, of course, because it's an indefinite integral. There's no bounds. All right, that's great. So I have this new answer, but we didn't start with u's, so we have to re-substitute our stuff back in. Instead of u, we look at what we have. U is equal to x squared minus 3. So we replace u with what it's equal to, x squared minus 3. And we have plus c. So that's what this integral would look like. And let's actually go back up and take a look. Well, hey, look at that. This right here is actually the problem we started with. They just put this piece over here. That was this function right here. If we integrate this, we get this thing. Well, derive this, we get that. So integrating this, we should get that. And that is exactly what we have. So that makes me feel very confident that we did this correct. And we can go on to the next problem. So this u-substitution idea gives us a way to kind of take these larger, complicated functions and turn them into really nice functions that we can maybe just do the power rule with to find these antiderivatives. All right, so generally your problem solving strategy looks like this. Look carefully at what you're integrating. Look for some function inside of something else that we can make equal to u. Take the derivative of that u and then figure out what we can do. Sometimes we might have to move some things around in our derivative of u, and we can kind of play with some stuff to make this all work out really nice. Hopefully you can reduce this down to something that you can evaluate an integral of in terms of u, and then you replace back. Okay? So looking at this next problem. All right, I see a 6x on the outside, and I see all of this stuff inside of the fourth power. Now, in my mind, it's this stuff that is really going to cause some issues. Step one, truly to solve this thing, if you wanted to, you could raise this to the fourth power. Like, we could do 3x squared plus 4 times 3x squared plus 4 times 3x squared plus 4, and then multiply by 6x. You could just distribute this all out. Get this giant, it'd be 2, 4, 6, 8, ninth degree polynomial, and then do the power rule. That would completely work. But that's so much work. That's tons of evaluation. So the u-substitution method says, hey, take this inside, make that your u. Usually the stuff that is inside of our function, that's kind of inside of some parentheses, inside of the bigger picture function, is going to be our u. If we derive u, that means derive this thing. The derivative of 3x squared plus 4 is 2 times 3, 6x, take away 1. And then derivative of 4 is just 4. But dx, because we took the derivative with respect to x. All right, looking at this thing, we wind up with the integral. Right now I see 6x dx on the outside. And look right there, 6x dx. Well, 6x dx is equal to du. And this stuff all became u to the 4th power. All right, this is super easy to integrate. We make that u to the 5th over 5. That's our power rule. Plus c, of course. That's a super easy integration. Now we just substitute back our u. Perfect. And if you want to, you can always double check. You can just take the derivative of this, and you should get back what we originally had. Thank you, Fundamental Theorem of Calculus, Part 1. Okay, so if we take the derivative of this, we would bring down this 5. Okay, so I'm just checking, making sure that we kind of have this idea. If I take this and derive, it would be 5, 3x squared plus 4 to the 4th over 5. But then take the derivative of the inside, chain that on, 6x. Derivative of c, derivative of a constant, is gone. Those 5s would cancel out, and I do see 3x squared plus 4 to the 4th times 6x. And if you just rearrange the 6x where you want to put it, we do get back to that original. All right, taking a look at this next example. All right, I see something on the outside, something on the inside of a larger idea. Again, we could just square this thing, multiply it all out, do a bunch of power rules. Or we can try this u-substitution. Usually the most inside piece is what we are going to have as our u. Derive that u and we get 3x squared. And we derived with respect to x. Perfect. All right, from here, I see, hey, the 3x, dx, perfect. So I can integrate this stuff, becomes just du. And then this stuff got replaced with u. We still have a squared. So we've got u cubed over 3 plus c. Just remember, this is more of a family of functions. We're not doing this at a certain bound. All right, replace our u with what we called it. And that would be our integral. All right, our indefinite integral. Perfect. Hopefully we're getting a hang of this. Okay, I'm trying some more here. But I've got cosine squared over sine squared. Cosine squared over sine squared. Well, we kind of have some options. I see the sine is kind of the thing that's being squared. So usually the thing that's kind of more on the inside of our problem is going to usually be our u. So let's check it out. If I have u equals sine of t, and I take du, just see what happens. What's the derivative of sine? Well, that's cosine. Well, that's perfect. So u is equal to sine, so I have something over u squared. Okay. And cosine dt, that's exactly equal to du. So I'll put a 1 over top of this. Well, u squared is actually, 1 over u squared is u to the negative 2. So increase by 1, and then divide by negative 1. Replace what we have our u with, forgot my plus c. And we've got -1 sine. Oof, don't want to do that. That's not sine inverse. All right, let's just write this as a fraction. And we've got our integral. Perfect. All right, but these all worked out so perfectly. They don't always work out that perfect. For instance, let's take a look at this one. All right, same idea. I see something on the outside, something on the inside of something to a power. Okay, so my likely choice is to let this u be x cubed plus 5. When I take the derivative of this new function, I get 3x squared dx. All right, so this is great. I've got most of what I need. I have x squared dx, x squared dx. Problem is that 3. When it doesn't work out perfectly, we do still have to take care of that 3. So this is all I do have as part. So really, we can kind of mess around with this a little bit. We can move this 3 to the other side and make that a 1/3 du. Okay, so what I mean by this are what we truly care about is x squared dx. This part, that's part of this integral, can be written as equal to 1/3 du. So when we come here, we say, well, this stuff is our u to the 9th. That's what I liked. But this stuff, the extras, is not just equal to du, it's 1/3 du. So usually we can just put that 1/3 in the front, and then our du at the end. That is 1/3 times our integral, and we are okay. You can take a constant being multiplied and move it to the front. So we have 1/3 u to the 10th over 10 plus c. Now I should multiply my constant by 1/3 in this case, but 1/3 times a constant is still just a constant. That plus c is just a constant. So we've got u to the 10th over 30. And now we can resubstitute our u. And we have integrated this function. Okay. If you don't believe me, double check it. Take the derivative of that function, and you should return x squared times x cubed plus 5 to the 9th power. All right, keep going here. Some more examples. We've got z times the square root of z squared minus 5 dz. All right, usually the stuff that's inside is going to be your u. Okay, the most inside stuff, usually 9 times out of 10, that's going to be your u. So derive z squared minus 5. We got 2z dz. That's great. On the outside here, I have z dz, so I just don't want the 2. I can move that 2 over. So my integral becomes 1/2 du, and then a square root of u. All right, to integrate square root of u, that's u to the 1/2. So the 1/2 in front stays times, add 1 to our power, 1/2 plus 1, that's 2 halves. So 1/2 plus 2 halves is 3 halves. And then we divide by this. Well, dividing by a fraction is really multiply by the reciprocal, multiply and flip. So 2/3. which becomes, 2's can cancel there, u to the 3/2 over 3, and u is equal to something. U is equal to that z squared minus 5. Awesome. Oh, that just disappeared on me. All right. Last but not least, these can get a little weird. Okay. So looking at this problem, I see something that's the most inner of this function. I see that x minus 1 inside a square root. We integrate, and all we get is just dx. So here is the problem. Right now, when I kind of do this substitution, on the bottom, I got the square root of u. That's perfect, right? X minus 1 inside of the square root. Du is equal to dx, so this dx becomes du, but I still have an x on the top. And that's not going to allow me to integrate. I can't integrate when I have x's and u's. Okay, so one additional trick. This thing right here, remember this u equals x minus 1? Well, let's rearrange it a little bit. Let's add 1 to the other side. And that's some way to write down our x variable in terms of u's. So this x can go away. And now we have u plus 1. Now, still looks pretty terrible compared to some of these other ones. I don't see how I can easily do a power rule. The square root of u, I could do that. This was super easy power rule. Integral of this, super easy power rule. Power rule. These became really easy. This one still doesn't look very easy. It's still a large fraction. Well, some just algebra tricks that we have. Remember, square root of u, that's u to the 1/2. Right? Well, it turns out you can split apart a fraction when it's addition or subtraction on the top. Do u over u to the 1/2 plus 1 over u to the 1/2. Well, u over u to the 1/2, we subtract those two exponents. And u on the bottom, that's u to the negative 1/2. So we can turn this one into a power rule. This original one, when you have x over the square root of x minus 1, since that x minus 1's inside, and you have this larger thing on the bottom, you can't split up a square root into two smaller pieces like that with subtraction, and then dividing by that just doesn't work out well. So this lets us change that to a power rule, and we can do that. U to the 3/2 times 2/3. Remember, same change, flip, multiply by the reciprocal. Instead of dividing by 3/2, multiply by 2/3. All right, add 1 to negative 1/2. That's positive 1/2. Divide by 1/2. That is actually a times by 2 plus c. And then resubstitute back in 2/3 our u, which was x minus 1, plus 2 times our u. And there we go. You can do some things with this if you'd like. For instance, we could maybe factor this. Again, we'll try to make things look better if we can. We could factor out a 2 from both of these two things. And x to the x minus 1 to the 1/2 power. So 2, they kind of both have halves, right? That's 1.5, that's a half. So maybe you could factor out the x minus 1, square root, half power. All right, that would leave, let's see, x minus 1 to the 2 over 2, or just the first power, over 3. And then we took the 2 out, we took the square root. So there would still need to be a plus 1 there. Not sure if that looks a whole lot better. We could maybe make this 3 over 3. Add that minus 1 and that 3. And we could maybe make it look like this. If you really wanted to, we could move that 3 to join that 2. And wind up with something less like that. Really, it's your choice on how far you want to go to make this look better. A square root times something is never going to be a pretty thing, but it's more of a matter of how do you want it to look. Do you want it to look as 2 smaller things being added, or 1 larger thing with some multiplications? All right, last but not least with this idea. Where is that? Let's put that right where it belongs. Interesting. All right. Last thing on the agenda with these u-substitutions, when we have a u-substitution with definite integrals, the goal is, I guess the main idea is, you can do it one of 2 ways. All right, let's just try to do this u-substitution, see what happens. So I see x squared on the outside, 1 plus 2x cubed on the inside to the 5th. Well, usually we're going to put that inside as our u. And that's perfect. Derive a cubic, you get a squared, and the squared's on the outside. Well, I don't want that 6. Okay, so we're rolling here. 1/6 integral from. Here's where life gets crazy. Let me erase those for a second. We wind up with du and u to the 5th. We don't want to write 0 and 1. These aren't 0 and 1 anymore. These are like x equals 0 and x equals 1. We need to kind of understand that. We've changed our variable, so we can't use 0 and 1 and just write 0 and 1, because these aren't, it's not the same variable anymore. We're dealing with u's. So you have one of 2 choices. You can write that x equals 0 and x equals 1. You can do your integration, u to the 6th over 6 times 1/6. So 36 on the bottom. Whoops. Okay. And we're doing this, it's a definite integral, so I can put that line there of x equals 0 and x equals 1. Okay. So you have 2 choices once we are here. Okay. Your 2 choices. You can substitute back your u. So we can say this is 1 plus 2x cubed to the 6th over 36. And now I don't need to say x equals 0 and x equals 1. I just put 0 and 1 because we're back with x's. Your other choice, I mean, we got to plug in 1, we got to plug in 0, right? So plug in 1, we get 1 plus 2, that's 3. 3 to the 6th power. Is that 243? 729 over 36 so 81/4 minus, plug in 0, so 0 cubed is 0 times 2 is 0 plus 1 is 1, 1 to the 6th. So 81/4 take away 1/36. We get 182 ninths. Wonderful. All right, that's great. Now, the other option that we could have done, instead of going back from u's to x's, we can leave the u's, but change our bounds of integration. These were x equals 1 and x equals 0. Well, plug in 1 right here. 1 plus 2 times 1 cubed, 1 cubed. All right, that's 1. 1 times 2 is 2. 2 plus 1 is 3. And we can just change that to a 3. Plug in 0 right here for this x. 2 times 0 cubed is 0, plus 1 is 1. And now you can just plug in 3 and plug in 1. Math turns out exactly the same. Let's see. 3 to the 6th was 729. Divided by 36 was 81/4. And plug in 1, we get 1/36. So the math after that all turns out the same. But do you want to plug in numbers to this larger equation? Or do you want to plug it into a larger equation and then just change your bounds? You really kind of have that choice. Okay. All right, finishing up this last example, we've got x times e to the 4x squared plus 3. Well, I know what I want for my u. That is going to be that exponent, 4x squared plus 3. du 8x dx. Well, I don't have an 8x dx in this thing. I just have an x dx. So I need to move that 8. All right, so when I go to integrate, I'm going to have du and a 1/8. Okay, that's my x dx, e to the u. All right, my bounds. I'm going to go ahead and change my bounds right now. If x is equal to 0, then I put 0 right here. 0 squared times 4 is 0 plus 3. I'm just going to go ahead and change that bound to a 3. That's a u equals 3. If x is equal to 1, 1 squared is 1 times 4 is 4 plus 3 is 7. So we can just change those bounds right away to u's. All right, integrate e to the u power. Well, that is just e to the u. And we've got from 3 to 7, 7 to 3. Well, inputting that, we got 1/8 e to the 7th minus 1/8 e to the 3rd. And that's about as good as that can look. If you want to make it look a little bit better, you could maybe factor out the 1/8 e to the 3rd. That would leave e to the 4th minus 1. Either choice, they're not looking pretty. But we can type in either of these. 1/8 e to the 3rd times e to the 4th minus 1. And we get 134.568. All right, and that works. Now, while we're here and we've got this nice fun answer on our screen, Let's just talk about how to use this calculator to maybe do some of these integrations. If we just graph what we're trying to integrate, x e to the power of 4x squared plus 3. All right, our goal is to integrate this thing from the bounds of 0 to 1. Let's just take a quick look at this table from 0 to 1. Oh my lord, this thing is all the way up here at 1096 after that. So let's change this. I need maybe just from -1 to 2. My y minimum, -6, that's fine. My y maximum needs to be up at like 1100. All right, so I zoom super far out, and here is what I am seeing. Okay, my goal is to integrate this thing, so I want the area between the x-axis and this graph. Okay, so I want this. My calculator can actually do this and find just the values. Okay, super easy. I go to this button here that says calculate, second trace. Option 7 is an integral of our function. All you have to do is just tell it the bounds. The bounds were from x equals 0 until x equals 1. And it will even shade in that nice little space there. And it will tell us at least the value of this integral. It won't tell us how it got it. It won't tell us anything else. But it can double check the value of integrals. Definite integrals, which is a nice little trick, a nice little thing to know. Problem is if you don't change your bounds, I think if you don't change your windows, some things start to get a little weird. Right, let's say we didn't change that. I think it messes up our bounds. No, it told us just fine. Never mind. Okay, so you don't even have to play with the bounds all that much. To get a review, you got to change your bounds, but we can do that there. All right, so a nice little way to kind of get around and double check some answers for definite integrals using our calculator. All right, that is it for that. You've got some assignments on 1.5. Good luck.